Yes, sir. Could you please acknowledge my voice and sharing both are
Yes,
fine?
yeah, both are fine, sir.
Thank you, sir. Well, we have seen morning session related to timing related, and now we will analyze power related and power related tool. It's an industrial standard tool. When we come to power analysis and all, it's a vast area, very big area, and people have been a lot. They giving more as a team. If you see design cycle, they are giving a lot of importance to this power analysis. And so all the phases like RTL code also, nowadays the tools are there to estimate. Normally it's not real values will come here at the post route power related consumption and all, but the technology has people have been estimating at the RTL code itself, and then they are every stage simulation using VCD, they are changing switching activity or your standard cells, they are calculating switching power, estimated power there also. And then after synthesis also, in the synthesis stage also, you will get the overall power report, not you won't get it at synthesis, but only you will get the standard cells. Each standard cells it has a power consumption and unit power consumption and other things based on constraints it will give. Then physical design. So in the physical design also, each and every stage you can be place it out to power consumption, whether it is a met or not, or maybe it is within your limit or not. So let's what are the flow means, if you see that power analysis, you have the chip level and then block level. If you go chip level, each network, metal layers and all have resistance values. So you have to extract RC. Once extract, and you will find that IR drop when you are signal traveling. So calculations of this power consumption, three main parameters. This also means, especially voltas, will give you three components in the power. So I'm not going technical details about low power techniques and other things. I'm just taking that components and show you the demo, because you guys means you all know very well then, because as a part of your syllabus you might have studied come across a lot of low power related subjects and all. So for this one, for today's this second of session, I'm going to give you tool demo. So tool oriented, how to get the power consumption related details and all. Hopefully this is going to be helpful for you when you want to be submit papers in journals. So the tools are optimized, and even morning session also you can using the timing sign off, you can also produce that same report, whatever we have seen that report and the terminal or some kind of a graphical user interface related reports, all are acceptable. So it's like a cadence is a very industrial standard, and all across all publication houses like Springer, IEEE standard, and elsewhere, all people they accept the reports from these tools. Yeah. So three main components are leakage, internal, and switching. We'll see what are the in details about. In short, we can say leakage like when you are uh, uh, when your device, CMOS device working, leakage means it happens. So it has a leakage power consumption. Earlier, 90 nanometer and 45 nanometer, no worry about that leakage power. But when you go to a lower technology node, this leakage power has a very crucial. And then internal when it is a even if it is on, the tool may not even when it is switching or it is on or off, internally it consumes the power. So internal power and switching, when it is a switches happens, no, 0 to 1, 1 to 0, sorry. So switching, these all terms, the terms basically extracted from the how the behavior of the circuit, and the keeping as a standardized components, leakage power component, internal power, and switching power. So optimization of this analysis and optimization of this EM and IR drop, including full chip. EM means migration. So the IR drop, especially IR drop, we will analyze because EM, there's a very, it's required a lot of data preparations and all. So in this demo, we'll go for the IR drop analysis, and also it is going to be impact on the power design closure and also total package to PCB. Properly planning for the power analysis. So basically, power analysis all started with the power planning. After, let's say, like a placement in our inverse, in the floor plan later, when you have the step called power planning. So the power planning contains that a lot of impact on your physical design when you go for power analysis. If something is not controlled in the last minute, like after routing, so you have to go back to again the step in the floor plan, or you have to be distribute your network, power distribution network, or maybe you have to increase the number of straps, or you maybe have to width of the metal layer to be increased power related components. Means maybe metal layers. You can be play with the higher metal layers which has a less resistance, so that you will get the less IR drop when you are in. So these all things are going to be impact when you are doing. So the tool voltage we are going to see here. If you see this VCD, value change dump, or switching activity information file, I guess this one, safe and these two files, based on your test bench, you write your design .v file and test bench .v file. Based on certain combinations, switching activity you will store in the .vcd format. So this .vcd format, a simulator can extract based on how much your signals are actively switching for a particular, for a analysis, like any statement. If a always inside always statement in our RTL code, in always statement, so many signals we will call, right? So let's like in a sensitivity list, if something changes in one signal, all signals update. So that kind of thing, each and every signal switches from 0 to 1, 1 to 0, how fast it is. So based on that, files we will dump into VCD, and then that file will be power related tools will be read out that file switching activity, and it will calculate. So it's all calculation only, not a real power at the simulation. SIF also, switching activity information file, is equal to the VCD file. Here, for our voltas, you have the IR drop analysis, power analysis, and EM analysis. So this is the we are going to check means IR drop analysis and power analysis, these two. And what are the inputs for this IR means voltas to layout? We require netlist file layout. Once the layout expected netlist file, so it's like a routed.v file, and then we get the power reports. So power reports in terms of these components: leakage, internal, and switching power. So if something leakage is more, then you have to think about whether your power planning has to change in the physical design, or you have to go back to your clock gating or some kind of low power techniques you can be. And also the tools, Innova's tool have inbuilt low power techniques like clock gating, power gating, and all. So it will be without user or without designer involvement. When it is a doing for placement and all, it's try to be also take decisions on the clock gating. So it's try its level best to optimize power. Yeah, now we'll come to IR drop analysis. So IR drop basically it's when power supply distributed uniform throughout the metal layers like VDD and VSS. Okay, so in your chip area, so metal layers have obviously it have an infinity amount of the resistance. So because of that, you will get the drop, IR drop. So this voltage applied to the metal wires also. This metal wires means interconnections, and the current starting flowing from the metal layers, and some voltage is dropped. Internal wires also. So you can, I think some of the, okay, one second. Yeah. So this drop, it's all about metal resistancy, and when it is a power signals going, so this is called voltage drop. You can see this VDD, this is the voltage drop here, and also ground bounce effect also, some extent. It will means it will be impact your values. So if you see here IR drop analysis, let me go zoom out. Okay, yeah, here IR drop, you have metal 1, metal 2, metal 3, three metal layers are here. Mm. So in IR drop here, let's we are just it's time, due to time factor we're not able to cover this EM, but we'll see that IR drop. So if you see the IR drop related here, you have metal 1 here, metal 2, and metal 3. So each metal layer have, you can see 2.9 volts voltage, and this metal 1, 2, each metal layer voltage earning, and each metal layer have its own resistance. So it's how drop will be happens when is your, due to the resistance. So you, if you see the supply voltage in y-axis and time in the x-axis, so when your power up time, so this is the like a normal voltage time, then it will be excess. So you can categorize that drop. Normal voltage is 10% if you take. This is normal voltage in the 10%. There is a 3 excessive wire drop. This curve has excessive wire drop, and middle one is still excessive, and then other things is acceptable, and the lower one. So we try our level best to be decrease the IR drop acceptable level. So still means so many engineers they try a lot of efforts they will give to be bring from the excessive IR drop to the acceptable levels. So the drop in supply voltage over the length of the supply line or metal layer. So the resistance matrix of the power grid is constructed. So this is constructed whenever power planning related stage. Average current of each gate is considered also. So this data will get from the .lib file of each gate current data. And matrix is also, you have LUT lookup table related values to be get the IR drop. It will calculate the IR drop. So these are the voltage levels. Ideal voltage level we expect like this line, but actually voltage level is like a minimum tolerance also. We should be consider this. So there are two types of IR drop analysis. One is the static and dynamic IR drop. We'll see the static IR drop analysis. In this also, two things we little means dynamic to IR drop to require a lot of PG network like a power ground, and there is a data to be prepared. So instead of we can take this
I think
time for analyze
last
static
year
IR
in the
drop
data.
analysis. Yeah, I hope some like okay. Yeah, and in the what is the difference between these two drops? You know, the first static is basically vectorless, and dynamic vector based. So this is the main difference we can. This is how actual power analysis, static power analysis. If you see, it will comes with the total power in terms of internal switching, leakage, and also down you will find the total power, and percentage also based on percentage. So here it is contributing internal around 80%. So they have to work on the low power, internal switching, means internal power optimization techniques and all. Switching only 16%, remaining leakage 3%. So this is how based on this component and means sharing of the each component, one can work on the low power designs. So next one is you have the grouping, sequential, combinational, or input or macros type. So here sequential cells, how many? So total sequential cells related each component, internal, again switching, leakage, and the total power and percentage. Earlier, this side total power components, and in the group you have means each and every like a if you have the macros or power pads or combinational or sequential, clock also consume more. So clock is the main major one. If you have more clock switching activities, power will be consumed more. So you have to be planned very well for this clock network. Otherwise, you will be ended up with the lot of power consumption from the clock component. So next one, rail. So when we are designing power plant, we have VDD and VSS, right? So VDD rail and clock when CTS time. So this rail related voltage, again voltage, how much voltage you are applying, then what are the switching power component, and this percentage also it will be covered. And down, if you see this one, signals, individual signals. Let's say like in your clock, in your design you have slave clock, master clock, block clock, or something like a clustered clock or C clock. So four different clock parts are there. Each clock which measure how much it is contributing. So that details also you will find. So the difference here you can see it is in detailed. Normally it's in detailed. Voltus you have, you will get power report from the Innovos and Voltus. Both are the here Voltus also part of Innovos only. And I'll show you once it is open the tool, we will see that difference between the Voltus tool and the Innovos tool power report. So this is the IR of static power analysis color coding with the different color code. If you have red color, it's a worrying thing. That's it's a above excessive IR drop if red color. So the blue and all, it's okay, acceptable and all. So you will get this power report. One thing you can observe here. Here we disable the standard cells. Only we are looking at the stripes, rings, and the power network. These are mesh power network. So power related, all this power IR drop mainly analyzing this metal layers, power network metal layers, power distribution network in internal in our blocks, or the sitting arrangement for your standard cells and all. So we need not worry about the power report in power consumption in the standard cells because it's already predefined cell. So here only we IR drop static analysis will be basically and the power network distribution network we try to be minimized. If any more standard cells are sitting in the one place, that will create congestion. So congestion also help your drop more like you have to be distribute that congested. So let's say like if you are all the standard cells are sitting in one place, so you need to be distribute or need to be spread it across your core area, then only your means the power signals will be properly routing, and then you can minimize the higher drops. Result browser will give each metal layer and how much, whether it is a ground or VDD, and related IR drop. So IR drop values it will be show that. How to fix this IR drop? So it's like a, let's say like after analyzing the IR drop, what are the action items will be change your or fix the power related issues, IR drop issues. First and foremost, spread the macros. So when you this means that you have to go back to your placement, or you have to go back to your power planning, floor planning. In the floor planning you means going to be place the macros if you have macros. So we should have to be take the decisions, macros, which are the macros required to be placed. Let's say like one instance I want to tell you. Here there is a macro, this is my block here. Total I have four macros here. Macros means it's a memories or some predefined already blocks. Okay. In these four macros, we need to see like a standard cells are here. standard cells. Okay, this all standard cells. Which macro have more connections with this standard cells? And some macros will have like a power is coming here, VDD and VSS. So power hungry macro, if it is a power required more for this macro, you have to place nearby this place. So if this macro is connections to more standard cells, then you have to keep this macro in middle of your core area. If this macro doesn't have much connections or fly lines, this called a fly lines or interconnections. Logical interconnections fly lines will be show when you are floor plan time, when you have the macros and all. So when you now sir, excuse me, Iljan sir, sir, could you please accept one of our team members going to be joined?
Yes, yes, accepted. Yeah, I can ask them to join.
Thank you, sir. Yeah, I'm sorry. Next, spreading standard cells. So here also, this is also placement. Let's say like these standard cells have more connections to these IO pins outside here and there. So then you need to be distribute these standard cells in middle or not one side. If you keep one side, what happens here? And entire signal routing happens here. Routing resources going to be congested. Then obviously it will be drop increases or higher drop as congestion issues and many other means factors. It will be going to be impact your power related sign of uh, power reports. And also next one is the increase the strap width. So when you do the you have required some calculations. Let's say like how do we determine this width of the power VDD and VSS? It has its own mathematical calculations. Let's say like you need to know how many number of standard cells, area, and then macros, then utilization in your core area, aspect ratio or utilization. Based on that, you will get come to know that value for these straps. Okay, so I'll show you one example for power calculations. Yeah. So you have mathematical calculations required for power planning time. So it's all like a not just like a default values. So we should be each and every strap and mathematical calculations. But normally it's like a it's required efforts. See, yeah, here it is. So if you have metal 4, metal 6 and 4 VDD strap, metal 4 and 6 is VSS strap, and here metal 3 and metal 5 and 3 straps are coming. So if you have the this one is like if you are congested one, you need to be distribute this logic or this metal layers width, this metal layers width and the spacing between these two metal layer straps also. So this is the calculations. Let's say like you have the frequency, operating frequency, how much operating frequency you want to be run, and also you voltage at what voltage it is running this. So let assume that here this is the calculations, power ring width calculations. So we are creating this ring, power ring, means outskirts, like you can see the outer our core area. So it's like a this power ring calculations. How do we arrive? First one is the required, how much gate count. This value we will get from the synthesis netlist. So how much it's now in this example 70,000 K standard cells, and how many flip flops? 4,000 here in this case. and the percentage of the flip flop with the dynamic gated clocks also consider, and the current needed for one how much frequency it is running. So this value we will get from the technology library. So zero point 0.2 milliamp per megahertz. So this is the input files required. So now if you calculate gate count, for example 200k, if you assume that no gated clocks and this clock frequency you want to run 200 megahertz, then current needed 200 by 70. So because this gate count is 70, and then zero point 0.2, this is the current zero point 0.2 current needed, and the 20 megahertz clock, and then um, you based on this two current needed for this, and 26.8 22.86 milliamp, and this you have the PG width. So power and ground ring PG width. This ring, it's like a, this is the value we arrived. So it's you this calculations, if you are multiply with this current density and you have this value, same value, because 1 milliamp per meter. So it's this based on this calculation only we have to be get this width. Otherwise, later stage it will show you the IR drops. And also stripe. Let's say number of stripes. How many stripes you want across your core area. So this is the power ring. Uh, Power ring is outside of your core area. Then this the red color straps and the power connection. This straps is basically to tap the power from the core ring and to give the supply to the standard cell sitting in your core area. So for these calculations, one strap set is 100 micrometer distance. If you assume core height and width, you have already these values when you are planning for your floor plan time, and then number of sets are added 15. So you can also have this one core and IO power pad selections. Also one set core power pad for it can provide 40 to 50 milliampere current for 3 to 4 IO means signal pads or your design pads. So it's like IO pad and core power pad. So both are different power planning. So core area you have IO power planning here for your chip level. For a chip level IO also you require power planning for corner pads and also signal pads here, and then this pad connections to this connections also you need to be give that. And as per some of the technologies they mentioned that 3 to 4 IO pads required one set of VDD and VSS, and 6 to 8 input pads, output pads, input pads required one set of VDD and ground. So this is how these calculations are also it means matters when you are means avoiding this IR drop. So increase the number of straps. If you also if you want to fix this IR drop, only. So you can, if you are increase the higher more straps so that all your standard cells and this power network will improve in your core area. And this creating power grid in higher metal layers. So this is the thumb rule. Almost all the technology files they go for higher metal layers. Excuse me. So higher metal layers means highest metal layers is preferred for the power grid. So it will have less resistancy, then it will be easy for you to be get the PG network or power ground network. So and also use multi-VT cells in the design to optimize the leakage, and also high VT cells in the non-critical path, critical path. So critical path, if you have non-critical path, different VT cells. So these VT cells are basically will get from the technology foundry. And also power gating, clock gating. Power gating basically you will turn off the particular group of logic, so which is not active certain time and all. So it's like a power gating, clock gating. These are the techniques you can be avoid the IR drop. So yeah, so this is the theoretical background. Now we'll switch to demo. If you have any questions, feel to ask.
Dear participants, if you're having any doubts as of now on a voltage IPR drop, anything, just you can ask me.
Yeah, okay then we'll continue. So I'm closing all the timing tempers. This is a morning session related all the windows I'm closing. So this tempers will come up from the tempers. This is the path analyzer, timing path analyzer. So we are taking the same design, our same design UART. So let's enable all the standard cells. Okay. Yeah. So when you it's a planning like a how do okay it's still taking time to close the tempers. So power planning is not happen in the last minute. It has a lot of planning from here. Let's say like here you can see power planning when you are getting this add ivory. So this values is um, so you can see this width and spacing rule. So you need a planning for this. Okay, and also when you are preview you have to be and also core around, and if you have some advanced or you can also see when you are placing and routing, let's say placement time also there is a optimizing for power. You can see optimization. So effort level, you can see power effort, none, low, high. So leakage to dynamic ratio 1. So they can like you can also go for I. So low. So presently it's a none. We gone for the timing driven network in earlier, like when you are cell placement and all. But now when you are doing for power optimization or low power URT, if you want to realize, you have to be go for high optimization effort, so that it will also impact your timing. So because timing and performance and power are the inversely proportional. If something, if I fixing means a low power, if I want to realize, obviously I have to sacrifice my performance, or else if you want to be realize your URT high performance, and you have to pay for power. So this is a inversely proportional, but as a designer we try balancing between these two. There are some in the inbuilt tool also will help you to be realizing the low power optimization techniques and all. So let us assume that these all are we have done our level best when previous steps and all, and we are now at the routing. So just the same design when we have taken in the morning for timing analysis, same stage we are taking for power analysis. Here also you will get the power analysis in inverse. So inverse also in this is the inverse. Basically, inverse will be taking care for physical design layout, and basically it concentrate on placing and routing of your design. So, but when you it is also give the power report, not in detail, in detail. Like let's say this is our power already we are in the inverse. If I ask this inverse report oh, power report, it's a give summary kind of details it will give. So you can see. So yeah. So setup, you can see this zero point 0.8 VDD and all. So we have done these setups, that's why it is taking consider. But in normally when you go here in the user, you will also have power analysis and power planning. So these are the basically it will give the overview report, not in detail. So let's say like if your power grid, power analysis, histogram and all. So if you want to go in detail report, then we required voltas. So for voltas, we required the routed network. So this is the routed network. And then when the routed network, you can see the congestion. So this is the congestion map in the overlay. So if you connect and you will find this report. So you have color coding here, congested area and all. So if you keep this color coding, particular red color and all, so this one, this area may have the congested routing. You can zoom out. So this area means you can congested area, you can be distribute network. So if you want to change this network at this place, or you can select this place. So you have only option, you have to go back to floor plan, then placement and all, or you can have to realize another placement. So congestion also it will have some impact on the your IR drop. So let's say now presently there is no worry about the congestion, because it's a, if you disable the layers, all the standard cells are properly aligned, there is not much congestion. But only this is the rows, you have each and every sitting row, need not worry, because it is a division divided one sitting arrangement to here. So but each and every row you have the spacing is there. So it's no, standard cells are placed properly without congestion. But only worry about metal layers like the wires or interconnections when this side especially. Okay, we will try to analyze this power report in voltas. So now to invoke the voltas tool, like we did during morning sessions for tempers, we can in standalone voltas. Before that, we need data preparation. So data preparation is nothing but, so we need to save this inverse data, routed data, save inverse, uh, this one, you are routed power, you are routed power analysis report, or voltage, you can keep it voltage input. So I'm saving this routed network or routing database to load into voltage tool. So I'm just storing DBS database system and UART routed voltage ENC in encounter. Actually, earlier version of this inverse called encounter. So still Cadence, they have been following this extension ENC. Other way also you can use INN instead of INC. You can use INN also acceptable. Let's save. So once you click on this now, um, in your background, so data is saving. This data is saving. So routed database ready to load into your voltas. Now you can see when it is routing time, zero errors, zero warnings. So its database is clean without any issues. Now we need same files, switching activity SDF file. So here write SDF file. So this all already generated a new file, updated file we can give. So uart voltas dot sdf file, generating worst case purpose standard delay format. This required power analysis sdf file also. And also we required spef file, because capacitance and RC components related information also we required, right? So we need to extract RC uart underscore voltas. SPEF file. So almost all, I mean, so four different files are required. So this one netlist file, SDC file, and then data, it's a SPEF file, SDF and SDF. So these four are ready. Now this right time we can invoke our Tempest tool, I mean, sorry, Voltus. So the same work directory I'm taking for Voltus. To invoke Voltus, just the keyword is Voltus only. There are like mornings in the various ways you can do analyzing this voltage, like a scripting based command line or graphical user interface. So we'll go for graphical user interface. Sometimes you can also require whenever your TCL files also help you to be immediately one run. Let's say like if you have in your work directly, so we have been loading from data from here. This is our current work directory. Inside you have means scripting files for the static and old dynamic old files. So yeah, here static, yeah, static power analysis TCL script. So after opening Voltus, you can also run this TCL script at once, and it will also give the static power report. Basically, it's read the libraries, left libraries, reading network, your sorry netlist file .v file, then your instantiating module name, spef file, dev file. So here dev file also required. I forgot to tell you the dev files, design exchange format, dev related file, where we get here, we will get from in the inverse, go to file, save, dev file. So dev file will give full details about your network or your routing resources, floor plan, standard cells, and all. So this entire data will be captured in the dev file. So it's a uart underscore voltage dev file will give you the files. So in the work directory, you will find these input files to voltage. One is the SDF file is here, dev file here, spef file. 1, 2, 3, 4, and SDC file for network. So before post synthesis routed netlist, and then means input file of this physical design, but actually we required this one. And also along with this, we have saved our database, routed database in DBS. So this one, you are routed voltage database. Inside your database, all the data, this will be automatically, tool will read entire your this data, and it will be power constraints and view definition files and all. So it will automatically come up with these settings also, the tool basic settings for power related analysis. Yeah, voltage open now. So we can also go directly from read the design. Otherwise, there is one command, it will be enable all this reading SDC file and all successfully and all. So let's same design I'm reading into voltage. The UART, this entire design database I'm loading into the voltage to analyze the power in detail. So here the command to load read design physical data DBS, then UART routed voltage dot in dot, and then top level name UART. So I've saved my database, routed database, routed underscore voltage dot in. So this is the file. Like so next, just okay. We can enhance this. Zoom in. Let's zoom in. So then I given enter. Now we can see the data is loading. All your means input files like a netlist file, and then routing stage till routing stage. What are the metal layers it is routed? All the detailed information it will be going to be read and into voltage. Yeah. 14 sync.0 clock gating. I don't have any clock gating cells in our core means our design. So it is saying and 14 sync pins, one source pins, and optimization also done, enabled RC. So power related load, power constraints, and all nano route mode, voltage IC power integrity solutions, giving some warnings, and here temperature 25 degrees and 125 degrees Celsius, and then some of the default values of RC value components. This is a part of your saving time. When your database saving time, it is already taken this consideration. Now if you see graphical user interface of voltage, now it is full. uh, its signals are means it's only power related or network mesh network, like a horizontal lines, vertical lines, and then standard cells. Okay, now we can also disable the standard cells instances. So this is you're going to be analyzed here. So in this voltage IC power integrity solutions, so the same interfaces you can find in the Windows also. So if you see these lines only available in this voltage also, same voltage. Okay, yeah, what we find here. So first and foremost, after loading this, you now earlier it was disabled this, so now you have to be enable, like you need to be read the SDC file, tool SDC file you have to give. So once this SDC successfully read into voltage, and then spef file, you are to voltage spef file, RC kernels can default it will take, and then SDF file or def file, SDF voltage LT SDF. So once you give this one, you can observe the same like earlier, how much resistive values, capacitance values, and all you'll find. See here, when you read spec file, so it's saying that number of resistors 2408, and ground capacitance 2528. Coupling capacitance are 588. When your RC extraction values stored in this spec file. So when this spec file loading, this is happening, and also SDF file also loaded, and other SDC file, SDF file, all things are loaded. Now, now after loading entire, you can read summary, get the summary of your in the voltage. Okay, if you have CPF file is a common power format file. So there is a UPF and CPF. There is a two type of low power formats are there. It's a scripting based. So if you have that add-on CPF files, UPF files, we can also give that and specify operate. You can also specify operating conditions. What is the slow, fast values, conditions, minimum max conditions. temperature, process, and voltage. These three parameters. But here it is taken only slow parameters because we are designing on the slow dot lib. We didn't consider the fast dot lib. You can also get the fast dot lib if you that has to be added in the synthesis onwards. So it will be taking decisions, minimum, maximum conditions. So once this is done, check the design. So check the consistency of the design, and it will be check the IO, netlist, physical library are all those power and ground related, tie high, tie low. So this entire files related summary it will give in the, and it will store in the check design folder. Click on it, check the log files. So it is, so it's saying that IO file is not a legal option for command check design options. So let's say disable the IO because we don't have in our design IO files. Only IO pins are there, not IO pads. So netlist and physical other things are okay. Yeah, still it is. Netlist is legal. Yeah. Okay. Well, let's see. Physical library, space coverage. This also little text only. So it's like a, some of the components are not required to be uh, add. So let's say power related ground. Okay, so fine then. This some of the files check here. It will be check design should be append already in their inverse tool. So here you can need not to check the in the voltage. Now get the reports. You can summary. So summary report. Some once you load it. So we have to set up before this check summary. So first and foremost here onwards, power power rail. So power rail, we have to go for this set power analysis mode. So once you click here, it is a static and dynamic. So we have two type of power we can categorize, right? Static power analysis, dynamic power analysis. So if you select this one, vector or vector based or vectorless, but we will go for a simple static power analysis, and analysis view will go for worst case and corner maximum. Okay. And then these are the static power analysis setup we done, and then click OK. Now, once this setup static timing analysis, next run the power analysis. We have done the power analysis mode setup and then run power analysis. Here, you need to give switching activity, input switching activity value, default and 100 megahertz to run dominant frequency. And other things are, if you have VCD file, you can give here VCD. But for we don't have that VCD generated file, it should be come with the Voltus run. Okay, output files, it should be, you required one folder, Voltus run here, the file name here. If it is not there, it will create. So switching activity given for static, because static timing analysis means static power analysis. Sorry, static power analysis means here switching activity will give the input switching activity and see that with the particular frequency value. So nets on the nets, and also here chip power, target chip power in the milliwatts or custom power. If these are the extra options, but basically we have to give these things and run. So it will running the static power analysis in the terminal. So you can find in detail report of the static power from starting from, I think, here onwards. Yeah. So is power analysis. It it is started. Okay, it is power set reset, and this is the command here. From here onwards, our power analysis, static power analysis started. If you are analyze, so um, yeah, so main part. So here it is taking the data inputs. Okay, so it's setting the static analysis worst corner, max create lib, and these are the default settings with our, and then set analysis mode leakage power, then here setting output directory as a reset and voltage run. So this is the output folder. So this entire ter terminal, like what are the terminal based script, everything is saved here in the physical design. uh, Voltage run, yeah, voltage run. So this is the report we can analyze. In this report you can see voltage IC power integrity solution. It is generated this static power report, and the library slow.lib library location, and the power used VDD and voltage VDD voltage 0.9 volts rail. So rail and parasitic used SPF file, worst case power analysis and all. So these all settings, considerations and all, temperature and voltage. Now you can see each and every cell in detail, power component, internal power, switching power, total power, and leakage power, cell name. So cell wise, so this cell wise report invoice can't give. So we can see here total number of cells are 128 cells. How much cell, each cell power consumption in detail we obtained. You may be surprised how it is calculated this internal sub switching and leakage power. So actually these components, let's say like here clock, let's see related this cell, we have lib files, right? It is all, everything is taken from the lib file only, uh, library file. So let's see that file in install foundry or technology foundry locations. I'm going. So foundry here, digital 90 nanometer dot lib files, in the dot lib, slow dot lib. Yeah. So this is the tech, all this entire voltas taken extracted results from this file only. So if you see the related particular related cell, the log buffer, okay, you can CLK instead of CLK. Yes, so we can see this buffer here, the power related, you can say rise power calculations and all, internal power, it is taken from this LUT, and also direction, each direction side, how much power, timing here, still timing, internal power from here onwards, fall rise time, rise power fall, and also internal switching. So these things it will consider from this lookup table. It's like a dimensional, I think, so it's like a lookup table. From lookup table it will be select based on your delays for the particular cells and all, index 1, index 2, transition. Okay, so based on that it will be select the power consumption, internal power consumption from this slow.lib. So if you feel like particular cell consuming more power, let's say if you want to consider sequential D flip-flop, so second cell, if you see this cell consuming more because point triple 0 0 6 1 6 2, other cells are little logic or different way, or you can also change the RTL code for this particular Means assigning to this cell, or you can realize with the different instead of RTL, different RTL coding styles. So low power RTL coding styles, if you are adapt, you can be avoid some of the more power consumption standard cells. So this way we can analyze each and every cells wise, and out of 128, each and every cell delays gone. This is one report. Another report you will find in the same year, combinational and sequential related information. So we can begin timing library for power calculations. So it is taking timing library for power calculations, and total estimated power, net and ground power calculations, and the timing window, the timing window data for power calculations. So these all uh, taking level and calculating our voltage engine background. So here the internal switching and what it is. So, and one more you can also run. Let's say here we have manually in the graphical user interface, we have run this switching, I mean, cells, each and every cells wise. Other way you can also source. Okay, if you see that source.tcl file static, you can also get the reports of that. So this is the file. Method and global activity. Let's say I am going again. You will see the difference between the, if I change the different switching activity. Earlier it was a switching activity. How much it is? So let's say mm, switching activity. Think uh, 0.2 input activity 0.2. Now we will change the value and see the difference. So when the 0.2, your power reports total leakage means a total power 0.026. So let's remember this number somewhere. Okay, let's keep this. I think already um, this report, we have this report, right? In this report, total out of total. So this is the total power report, I think, total power report. So you can save this, or instead of overwriting this one, we will change with the different name. In voltage run, input switching activity of 0.2. Okay. Now we will change that and see that if power, how power it is different. Static power mode. So this is the static power mode. Set power analysis mode method static. Now it is one. It is replayed one means it is set static mode. Then next apply the switching activity instead of 1.2. Let's decrease the 0.05 switching activities. So apply here. Now it is set 0.15. Then rerun once again the same report, or also you can say set power output directly, static power, and report. Mm. After this, you can in the graphical user interface itself run power analysis. Yes. Okay. Yeah, 0.15. Now When you have given this values, so output as it is generated report file. Now also we can see the changes. And likewise you can be different means constraints, you can get the different power reports. Internal, how much it consuming 52%, and switching leakage percentage also. Based on this percentage you can take the action for which component you want to be optimized. So each and every component have its own methodology to be optimized, or realizing the low power particular switching or leakage or internal type. Other next one is IR. Here, if you in the voltage, this is the switching activity. If you take IR drop analysis, set railway analysis, so it's here you can see early, static, and XT, and you can give this PG file. So it's tech file. So power and ground related tech file location I'm giving. So this. Then remaining other default, and then apply here. So next, now it is enabled. Earlier it was disabled. Now we can analyze, run rail analysis or analyze. So we have set this one, static rail analysis mode, and then uh, run. So in this run you can give this zero point 0.9 volts and threshold 0.85 default, some 5% less than threshold voltage, and remaining you can, I'm going only targeting one signal, power net signal, and remaining things are netted. Power current files. So this required to generate one PG files. So this file power current files also, you need one script to generate this file. Once you give this one, it will be accept, and it will check on the one signal if particular voltage and threshold model, and how it is going to be impact on the particular metal layers. And also you can see resistance analysis. And if you each and every cells viewer also can see, let's say in this technology, now if you add a, so this is the layout view of that. When metal layers, see this is a metal one. So when metal layer one, how voltage drop it will, uh, if you see the inverter, then easy for you to analyze. See, this is the two in single input inverter, and this is the VDD and ground, CLK inverter one. So these are the bigger design, D flip flop and all layout design. The schematic generated layout design. Okay, so this view, cell view, library view, we can see. And one more, if you go down here, you'll also plot, and also this text report, power density report, particular area power density report. You can select, and how if you draw this one particular line, it will give the density report and text format for power, and you can just click on this, it will create the entire report. So voltage run output file. Okay, it's generating output file. Yeah. So apart from this, you can also get the power analysis in the, yeah, it is updated now. It take time to be generating these different values. So If changes, based on changes, you can see the internal power related VDD and power. See sequential group, like in the slide we have checked, right? So we will get the static report with power component. Then after grouping, sequential, combinational, logic. Then after means power rail, we have given VDD zero point 0.9 internal switching and leakage of particular that, and the clock also. If you have one clock signals, it is a TX clock, and then clock related details also. So final distribution summary: highest average power and total capacitance, instances density, instances with the no power activity, and decoupling capacitors. If you have that power also in detail power report, we can get it from this voltage. So yeah, after this netlist statistics is related to the netlist file information. It will, yeah, what are the cells in netlist file? So you can see in the terminal primitive cells, number of instances, nets, and these are the statistics about netlist, about your number of cells, number of nets, and if you have any generated nets or try nets, pins and ports, IO ports and all. So this information also it generates, and that's all. Like you can analyze here, only analyze, and also once you analyze this one particular component you want to be optimized, then you have to go to your to this entire data, inverse extracted data, you can pass to Voltas. Then Voltas going to be read entire files, and then it will give the power report in details. So it's basically power to optimizing power. It depends on the planning, like iterations, and you need to first give the importance of the timing or power. So if it is a power, you have separate flow for power, low power flow, or in that case you can avoid the performance related constraints and all. So CPF, common power format, UPF, common power format related, all those things will be have it's a separate, it's have its own flow for the low power to realize your design. So this is how it's a basic check, means a basic power analysis using voltage. If you go in detail, you can find the rail, IO rail. For if you have, this is the block level only. For if you go for chip level, you have the IO pads related power analysis, and IO rail connections, and means connections like IO pad related rail connections, and also mesh network. Let's say if you are disable this net layers, so this all nets. If you are only you keep the power nets and nets. So disable and only keep the power nets. So these things like straps and power ring, this ring related analysis also, it have separate its flow for this one. And dynamic also, you will have the dynamic have both way we can run, either manually graphical user interface, otherwise we can have the scripting. So dynamic power T cell. So here we need to create the dynamic. Here also the same data we will load, netlist file and all SDC. Then instead of earlier power directory, we dynamic power related, and you will have the VDD activities, the particular values, and vectorless or vector, then you will find this simulation time also, resolution simulation 50 picoseconds for dynamic, and then we will find that report in dynamic.rpt. So you can also run this and it will give the power reports. Or let's say if you disable this one, okay, already we have run the static. So we loaded left files, lib, lib files, and also .verilog files, netlist files. So I'm disable this and we will run this file. Down is common for all the designs, only these input files are different. So here onwards common. So now save this in the terminal here. So here if you can see the history, you will find this, what are the commands here you have used. And also in your work directory command dot cmd and also log files will be created. So here sourcing dynamic power dot tcl. So now dynamic power related switching activities started calculating. So for this dynamic def file locations we require to be specified. We have generated the def file, but it is not given in the file power dot dynamic power dot tcl files. So if you give this one, you will get the accurate. Otherwise, it's also give, but so vectorless, you can also analyze this one. So number of simulation time and see the dynamic values are changing. So it's earlier static, it was 0.24 something, and now it is 23 for this dynamic. Okay. So various ways you can be VSD processing definitions, it will be extract from your netlist file. Okay. So yeah, with this note, concluding from my side. So you have any questions? Now we can discuss. It's like this one is we have kept for simple static timing analysis only. For in detail, it's required more time. So yeah, El Elren sir, are you there?
Yes, yeah,
Sir,
yes,
over
sir.
to you. If you have any
Okay.
questions, we can be discuss.
So, dear participant, if you're having any more questions related to the Voltas tool or about the Innovus tool or whatever is the study from the morning, template and any other tool, so kindly you can ask the research person, they're ready to help you.
So those who
So, any
want to
more?
be explore more about these tools, you can find in this flow or help documentation, and also if you have the course access, I think it's time. I'll take time to explain course access. You will find a lot of advantage when you have the course access. Cadence online support. In short, we call the course Cadence. So those who have the genuine license and customers, and they can be utilize this. It's a you will have a terabytes of data in related to say reference designs or application nodes, and also rapid adoption kits like a getting started, easily get start, all the tools and all. So it's like a one stop solution or one place, entire knowledge database kept here. So you can see here online courses, you can freely finish your means particular related courses like power analysis and all. So you can also see the rapid adaptation kits. This is getting started modules. So if you click on this, you will find the rack files. Rap means you have to choose that means here keywords to be shut out. Tempos, voltas. If you click on the voltas, then you will find power analysis. Power analysis. You can see power and rail analysis using voltas sign off. So if you click, it will come with the detailed documentation as well as the rack file. So it's a good thing about this. If you download this rack file, it contains required input files, 56 MB. So see here, uh, so using power and rail analysis using Voltas IC rapid adaptation kits, you have the steps. So you can see the static power analysis, loading the design and adding characterization and dynamic vector and powerless and early analysis. The same whatever we have done. So here, but in they have taken instead of UR tower design, they give their reference design. It's here filter design, FIR filter design, which has around 9,000 cells and generic 90 nanometer technology node. And if you they'll analyze this same thing whatever we have set power grid analysis, then they try to be and very interactive way. So it's also give the snapshots where you have to changes and then run. So this is the report you will get: left file loading and cell type power pins. Then after, if you follow these steps documentation, you will be uh, learn the entire means within less time. And initially with this reference design you can practice. Later once you are familiar with this flow, then you can be start using your design. So you can also see the power particular voltage. We have given one signal only, so you can see three four signals also if you are loading CPF. And then static power analysis, these are the commands. We have seen one static timing analysis mode, only one method, but you have several methods are also be there. So once it is downloaded, you can see the extract that file in your work directory. You will find data files, left files, all those things in the same place. And Voltas related scripting also you will get it. The best thing here, scripting and everything is a aligned model files, library files and all. So just if you follow the documents based on this directories, you can go and execute. So it's a dynamic power related power you have to enter in here, static power you have to enter, TCL script. So these are the TCL script to be down means developed. So you can also modify according your requirement if you. So not only means this is about rack, and this you will have the online courses bites, short bites. So you can 5 minutes, within 5 minutes conclusion videos also be you will find. Let's say like you want to see the voltage demo or voltage power analysis. All the EDA tools related demos you will get it, and it's all freely accessible. So those who are have the content they can be explored. So you will have this module, so talk about how to extract the or static power analysis feature. And then it's a very short 5 minutes. You can see 11 minutes.
Let's look at the ways to estimate or calculate
So
the
also they'll also give the
D
mathematical
star A
calculations.
star.
It will help you for you want to be more little more learn and explore in this domain. So and also technology files. Those, if you have this, you can freely download technology files, updated technology files, generic process design kits, and application notes, error messages. If you have, you have to copy paste here that ID, error message ID. You will find the relevant data, and the scripting of your TCL script and all available, and product manuals. So product manuals, if you click on e-manuals, then if you, one page contain all the videos, webinars and all in one place. Hold it as if you just-
Hello, Nagaraj sir.
Yeah.
Sir, actually for academic purpose, so is it GPDK 22 nanometers available? Can we work on that? Like anybody, if they want to do any research below 45 nanometer technology. So is it available for academic purpose?
Yeah, absolutely. See, actually, sir, proprietary PDKs are very costlier than tools itself. So normally, if you think you feel like cadence tools are very costly, but if you go 45 nanometer TSMC or even 18 nanometer TSMC, you ought to pay more than 10 lakhs and all. So that to ND agreement. So it's like a lot of things involved, an ND agreement and all. So if you are a bare proprietary related PDKs, if you get it, well and good. Otherwise, you can you can also use this GPD case. So normally, see, I think this right time, if you, I have published several papers with the GPD case. See, basically, many of the publications, they not ask which technology node you have been using. So they, if you say particular technology node, it's going to be publicity. So you have to say the technology, just 90 nanometer, 180 or 65 nanometer. So here, last year we published this paper in Elsewhere, Microelectronics Journal. You can find how the cadence tools help you to be published the papers. So here, ASIC implementation time, 90 nanometer CMOS technology. No need to mention whether it's a GPDK, TSMC, UMC, SCL and all. So if you are mention that, then basically it's going to be particular technology like a TSMC, it's going to be like a publicity kind of thing. So instead of that, you can just technology node. So if you search some documentation, you will find in GPDK 45 nanometer absolutely equal to the TSMC 45 nanometer. Only difference is this is only meant to be only for research and teaching, learning and teaching purpose for GPDK. It's only for not a fabricatable with this, because ultimately you are going to be end up with the publications, right? As an academician, or if you want to tape out only, you want to be tape out your project only, then only you have to go for your proprietary PDKs. Otherwise, it's absolutely okay with to use the GPDKs.
Okay, thank you, sir. So still the participant, do you have any more doubts? Any things you want to ask from him? Just you can go ahead. So he'll help you out.
And one more thing I want to be clarify all our participants. Let's say like we have been facing so many, when you are writing papers, you may be thinking that how lower technology, if you use lower technology, paper will publish, but it is not the case. See, let's say in my case, you can see in this paper publications, this is a research work. I have used 90 nanometer, but other designs, reference designs of various different technology nodes are there. So what you have to do, whatever the available technology node, you keep it the same thing and you do some kind of a normalization, normalization between the different technology node. Let's say like for me, I brought one equation for design efficiency. So this design efficiency doesn't depend on technology node. It's basically frequency, operating frequency of the design, or maybe it's architectural level, data throughput and all. So area. So some of the normal or scaling factors you have to bring, normalization factor or scaling factors, so that you can be compare your technology node. And many of the research, as per my understanding, even transaction papers also, they never even see you are using lower technology or higher. They only see the novelty. If your novelty is good in your paper, even 350 nanometer also acceptable. Only just you have to be find the normalization between the different results, so other reference papers for comparison purpose. Yes, yes, sir. Over to you, sir.
Yeah, thank you. Thank you for the information. Yes, the participants, it is over to you. So still, if you are having any more doubts, you can ask him. Okay, I hope there is no more doubts towards audience. So now this is a time to attend on our FDP 2 days FDP was successfully completed. This is a time to go for a vote of thanks. The vote of thanks will be given by Professor Hamsaleka, the Department of ECE, CMR University. Madam, over to you, madam. Before that,
Thank you.
madam, please go 1 second, madam. So before that, sorry, so I need some feedback from the participants for the FDP. Any participant, can you give your feedback? Any participants, please kindly give your feedback about the programs for 2 days.
Good afternoon, sir.
Yes, welcome, madam. Yeah.
Good afternoon, sir. I'm Professor Shilpa from Samram Institute of Technology. I've attended this 2 days workshop program which was conducted by CMR University. The session was really good and we were got benefited with this. I am handling a VLSI lab in the Samram Institute of Technology. Because of this session, I have learned lot many things. Um as well as the RTL designing yesterday in the afternoon session, they were teaching about it. I was earlier, really, I had some of the doubts over there, which got clarified. I thank all the organizing team who have arranged such a nice workshop for all of us like this. So we will be looking forward for such a nice sessions next coming days also. Thank you very much. Thank you for giving me opportunity yeah, to give the feedback over here. Thank you.
Yeah. Thank you, madam. So any other participants want to give a feedback? Okay, so yes, just let's move on to the vote of thanks. So I call upon Professor Hamsalekar to give the vote of thanks. Over to you, madam.
Thank you, sir. Good evening, all. On behalf of CMR University, School of Engineering and Technology, Department of Electronic and Communication, I extend my heartfelt gratitude to each one of you for making this faculty development a resounding success. To our esteemed facilitator and trainers, Priyanshu Datta, Field Application Engineer in Entuple Technology Private Limited, and Dr. M. Nagaraju, Technical Manager at Entuple Technologies, Bangalore. Your expertise and dedication have enriched our knowledge and broadened our horizons. Thank you for your invaluable contributions. A special thanks to our participants for our active engagement and insightful discussion. Your enthusiasm has truly made this program a dynamic and impactful. Our mentors, advisors, your guidance has been instrumental in shaping our learning journey. We are immensely grateful for your support. To the support staff and organization, your meticulous planning ensured that the smooth conduction of every detail. Your efforts have not gone unnoticed. Lastly, to our management and leadership, your vision for professional growth is deeply appreciated. Your commitment to our development is inspiring. As we conclude this program, let's carry forward the lessons learned and the connections made together. We will continue to strive for excellence. Thank you, one and all, for joining our workshop. Over to you, sir.
Yeah, thank you for everyone. So we'll catch you with another one more workshop in the future. Thank you to everyone. Thanks for your participation.
Thank you,
Thank
sir.
you.
Thank you all.
Thank you, sir.